All right, so this is the deep dive into the heart of computers, A plus hardware mastery. No problem. All right, so yeah, this is the training camp is just getting this webinar series off the ground. We've been so they were teaching classes well before I came on the scene in 2014. But this webinar series is a new idea. It's a way to get folks who already have their certifications, some quick and easy CEUs. So we're doing this, I think, for at least most of the CompTIA certifications, maybe even more. I don't know. So depending on what other certs you have that you're trying to maintain, yeah, you might be able to do more of these. So, and they may even be available. I think this is being recorded so that it can be done offline. Now, I don't know how the certificate of completion would work there. That'll be something to talk to like a sales rep about. They'll have the details on that. But looking at the screenshot from the CompTIA website, you see here A plus requires it's the lowest they have, 20 hours of CEUs over 3 years, which is kind of nice compared to especially the Sec Plus or the CASP. So you need 20 hours. It sounds like you've done this before, but 20 hours over 3 years, just working in computers and IT will get you, 3 CEUs per year, which is kind of nice. It doesn't quite get you to where you need to be, though. You're not quite at the halfway point just through work. But this webinar will be an extra 2. So then, that gets you to 11, and yeah. So it's just one step closer. You'll need, I don't know if you ever submitted webinars for CEU credit, you'll need an outline of the course. I can actually put that into a Word. I have it in a Word document. I'll share it here at the end, so you have a copy of it. But it's on the training camp website, and it's here in the slides as well. But they'll want like you just submit like an outline of the webinar training, and then the date that you took it, and then you'll need a certificate of completion from training camp. But you just sounds like you've done this before, but you just Google like CompTIA CEUs, and they'll give you like an evaluation tool that when you're done, it'll tell you to log in and upload the webinar information for your credits. All right, so here is the outline of the seminar or this webinar. We're going to do an overview of just talking about like basic computer components, stuff that I'm sure you're familiar with, but never hurts to get a refresher. Then we're going to look briefly at motherboards and CPUs. Then we're going to look at storage and memory, power supplies, peripheral devices, and then CompTIA's troubleshooting technique. Just a caveat to all of this again is like this is going to be focused on CompTIA level. What CompTIA focuses on for the A plus exam is what we're going to be focusing on here, and I'm sure you're aware that CompTIA is not. We'll make a couple mentions of newer technologies, but by and large, the new stuff has not yet quite made its way to the test, which makes sense. Hardware changes so quickly and the technology changes that if they were trying to keep the test on the bleeding edge, that would be even harder for students who are new trying to get into the field. So there is some delay between CompTIA and what the test covers and what you'll actually see if you went into like a Fry's Electronics or something like that. So section 1 is core computer components, understanding the roles and functions of the CPUs, RAM, motherboards, and power supplies, and how they work together to, quote, power a computer. All right, so I'm going to start with a slightly more philosophical question of what is a computer? Technically speaking, a computer is any device that is Turing complete. So Alan Turing was a mathematician in the early 20th century. He actually famously helped crack the German Enigma machine. They've now recently made a movie about him, and I guess was pretty popular. But he had this mathematical notion of a machine that could handle data manipulation, take inputs and outputs, and then do operations on this data. It was able to support conditional branching, which is a series of logical decisions. Loops and recursion are part of his model, and it has to have both memory and storage. So it's like a mathematical understanding of what a computer is. And there are non-electronic computers, for the record. you've got, your abacuses and your slide rulers are technically devices that would meet Turing's definition of a computer. This is what it means to be a computer, these properties, to be able to manipulate data, do conditional branching in software. I mean, Turing effectively invented software is what he did. Yes, the Enigma machine, the name now of the device they created to crack wasn't crack the Enigma machine, but it wasn't properly the computer because it was doing a very specific task. But his theories helped us develop the modern computers, and he effectively invented software. Um, in terms of core components of a computer, you're going to see they have processors, they have memory, they have storage, they have input devices. Now, we typically think of like a keyboard or a mouse, and that's true, but it can be sensors as well. Not every computer will output to a screen. Some of them will output to black boxes or other recording devices, but those still count as output devices. And then a motherboard to kind of keep everything together and provide the communication between the various components. And this is true whether you're looking at like a Raspberry Pi, like the Raspberry Pi 5, and it has like 8 gigs of RAM and one PCIe bus. Or you're looking at like the IBM Z series mainframes. Those things are amazing. 256 cores, 192 PCIe slots, 40 terabytes of RAM, 236 gigabyte L4 cache. I mean, those things are monstrous, but I mean, they share some of the same components and attributes as the lowly Raspberry Pi at the same time. They just obviously have a lot more of them. So all of these components, whether you're looking at a Raspberry Pi or a mainframe, are going to have these similarities in common. In terms of the processors, you have a CPU, and that is a general purpose. It's a device meant for general purpose processing. It's largely focused on arithmetic, logic and flow control of the operations. It's optimized for serial computing, doing one operation after another. In comparison, you have GPUs, which are divided into thousands of small cores, specifically geared for parallel computing. And that parallel computing and the type of the way they're optimized makes them great for the computations required to do graphics, because graphics are computationally intensive. And while CPUs can do them, turns out the GPUs just do them better. Also, it's really good for any kind of like mathematical modeling. So they get used a lot in science and cryptography, and they also get used in Bitcoin farming, which is one of the reasons why the cost of the GPUs went up so high in the teens and has stayed high, is due to the demand for crypto mining. So people just make farms of these GPU devices and crank out cryptocurrency. In terms of some of the attributes we'll see of processors, they can have multi-cores. With a multi-core processor, each CPU die, that chip, actually has multiple independent processors on it. Each one of them is acting independently, although they will share cache. At least a layer 2, layer 3 cache will be shared. And allows for parallel processing. It makes it possible to do both multi-threading and hyper-threading. So hyper-threading is Intel. That allows for a single physical processor to appear as two logical processors to the operating system. So with multi-core, you have a physical separation of processors on the physical die. With hyper-threading, it's a logical abstraction, treating one physical core as if it was two logical cores. And then with multi-threading, that has to be enabled in software. That is where programmers who write programs can leverage, writing multiple threads, and the threads will run in parallel, and then be processed in parallel. So that's you may be having your graphics done as one thread and the audio done as another thread, and user input being done as a third thread. There would be more than that, but just get the idea that these would each be running and being processed in parallel. So sometimes you'll see it with like a game's graphics and the audio get out of sync because they're being maintained separately. It doesn't happen often. The programmers can do race conditions and check to make sure that everything's working. But if something goes wrong, you can get those threads out of sync with each other. That leads to security concerns as well, but the idea of being able to do multiple threads is pretty common in a lot of applications these days, but it has to be enabled by the programmers, whereas the hyperthreading and the multi-cores are done in the system itself. Memory really is just a series of conductors used to store program code and application data. So it tends to be volatile. Not all of it's volatile, but the memory we tend to use in our systems, the DDR RAM is volatile. So since the 1970s, we've been using dynamic random access memory, or DRAM. There are a couple different types of DRAM. The original DRAM, it turns out, was not synced to the bus, to the system clock, which meant that you could get the RAM and the system out of sync with each other. When that happens, the system is making a request for memory, and the memory is not ready. So now the system has to wait, or the memory's ready, but there's no one there to take the information. So now the memory's waiting. In both cases, you have a lag or a latency, and that's not really ideal if you're trying to get throughput on a system. So the original DRAM was not synchronous, but they then quickly moved to SDRAM, which is synchronous DRAM. There's also this Rambus RAM, or RDRAM. It got used in graphics cards in the around the year 2000. And it also, Intel was trying at one point to make it a they're making motherboards that were using it, but that was a fight that they didn't win with the industry. So the industry moved to DDRM. I guess the advantage of RDRAM was that it was faster than just regular DRAM. But with DDRM, they found a way to get better throughput than even RDRAM. It uses something called double pinning. So basically, they found a way you have the system clock going, and you can send data, on the system clock in sync with it. But then they found a way to double dip. They found a way to send data both at the top of the wave and at the bottom of the wave. So they got to send two sets of data in the same clock cycle, which meant twice the throughput. And since then, they have, with DDR2 and DDR3 and DDR4, they keep finding ways to get more transmissions on the same, single clock cycle, double dipping, quadruple dipping. They just keep finding ways to etch out performance gains, taking advantage of the system clock. In terms of the packages that you can get within memory, you've got SIM, single inline memory. So I don't have a memory chip here, unfortunately, I can just show. But if you look at an old SIM memory chip, so a modern RAM stick will have chips on both sides of the stick. With a SIM chip, it's just going to be on one side. So it's memory. It was an improvement at the time, but people quickly realized, hey, wait a second, we're two sides of this stick. Why don't I just stick circuits on both sides and get more bang for the buck, which is what they did. But the original SIM, I mean, this goes back to the 70s and the 80s, had 30 pins or 72 pins, and only supported 32-bit architecture, because by the time we got to 64-bit architecture, we'd already gotten rid of SIMs. Then we got dual inline memory. That's where you put those chips on both sides of the stick. You have two sets of pins. There you have a minimum of 168 pins. And we're going to look at some of the newer memory. You'll have a lot more than that. But at this point, you have support for 64-bit architecture. And there's another variant of DIMM, which is SO-DIMM, or small outline form. It's a small outline form factor, specifically seen for tablets, laptops, and embedded systems in general. In terms of motherboards, they are the backbone of the computer. Their power requirements dictate power supply standards. So think of ATX. We think of ATX as being a motherboard standard, and it is. But the actual ATX standard also defines ATX power supply units, and that has been up every time they update the motherboards. They also update the PSU standards as well. One of the other things that it does is it has the firmware on the system to handle inputs and outputs from the various peripheral devices. It's where the BIOS or the UEFI is stored in firmware. So when you turn on a computer, it's the firmware on the motherboard that kicks in and starts running before an operating system ever gets a chance to load. If something goes wrong or there's a security, uh, you know, restriction put on in the UEFI or the BIOS, you won't actually be able to get that system off the ground if you can't meet those requirements. So we don't usually encounter that until there's a problem, but that software is there. And like any other software, it can get updated, corrupted, infected, etc. So there are some security concerns there as well. This little diagram has a decent picture of a motherboard. And you can see on the left-hand side here, we've got the I/O ports, including our USB ports, audio ports, maybe an HDMI port there, a bunch of different USBs, etc. You've got a CPU socket. Obviously, there's no cooling solution on top of that right now. This is what it would look like if you took it out of the case or out of the bag. Connectors for various optical media, memory slots, connectors for the hard drives, all of that. They all plug into the motherboard. So, in terms of the power supply units, the power supply units are kind of like the unsung heroes of computing. You never say to someone, "Oh, I'm building a new computer," and they ask, "Cool, what's your PSU?" Uh, just taking for granted that you'll get one, but they are really important. If you don't have enough power to run your system, it's not gonna be able to do much. So things that we have to consider are the fact that computers, uh, one of the reasons they're so big is that computers run on DC electricity, which is great for electronics, but it's AC electricity coming out of our outlets, and that's a problem. So among the other things that the power supply units do, they have to translate that AC electricity to DC power, smooth it out, and then feed it into the system, hopefully while avoiding spikes. So yeah, we get AC out of our walls. We need to translate that into DC. Obviously, you can see there's going to be fans in that. This conversion generates heat. In North America, we tend to get somewhere between 100 and 127 volts coming out of our residential outlets. And then in the rest of the world, Japan also is on our standard, and there are a couple like islands in the Caribbean and some other places, but it's generally a North America thing. And the rest of the world tends to use the 220, which can range up to 240. So back in the day, you'd have to, I don't know how old you are, but the back in the day, I remember putting together my first computers. Yeah, you had to actually, there was a little red switch on the back of the power supply unit, and you had to tell it what to expect. I mean, the good news there, especially in the States, if you inadvertently tell it to expect, 240 and you feed it, 120, it's not going to damage the hardware. Whereas if you go to Europe and you tell it to expect 120 and it gets 240, you're going to damage your electronics. And so that was the one nice thing we had in the States was we didn't have to worry about that so much, but still something that had to be kept in mind. Anymore, the power supply units are designed to auto detect and auto switch. So they will detect the current coming in from the wall, and they will make the adaptation as needed. You could still find, I suppose, PSUs that don't do that, but as to why you would turn off auto switching, just makes your life easier. So enjoy it. In terms of recent developments, this is kind of a neat moment, interesting moment in computer hardware that we're in. The TPM chips have become mandatory. Looks like we have a third person joining us. Welcome, Purini. I'm not sure if I'm saying your name correctly. Can you hear me, see me? Welcome. Can you hear me or see me? All right, excellent. Thank you. Welcome to the webinar. We are talking about some recent developments in hardware. So this is a 2-hour webinar meant to get you some continuing education credits in A+. So welcome. When we're done, if you've got some questions about how that works, we can talk. I kind of went over it a little bit earlier, but I know that people are just getting home from work and all that other good stuff. Yeah, no problems. All right, so yeah, this is an interesting uh moment in that we're at in terms of hardware development. So one, the TPM chips are becoming mandatory. UEFI legacy mode is becoming obsolete. I have a Dell laptop here that just informed me that I was not allowed to turn on legacy mode. And because it's running Windows 11 and Windows 11 is requiring those TPM chips. I got a notice then my desktop computer is admittedly getting a little old here, but it doesn't have a TPM chip, and Windows has informed me that it will not support Windows 11, or I can't install Windows 11 on it, I should say, and that Windows 10 is going to be reaching its end of life next year. So I guess that's going to be an invitation to just completely switch over to Linux. I'm not going to buy a new computer just to, because Microsoft has decided to retire Windows 10. We'll see if they backtrack on that. I suspect that it's going to upset some folks. But yeah, I mean, the UEFI has been around, for decades now, and there's always been this talk about requiring secure boot and security required by the TPM chip, but vendors just didn't jump on board, and Microsoft has finally decided to just go forward and deal with the fallout and require the TPM chip, which is odd because I can run Windows 11 in a virtual machine. I just virtualize the TPM chip, but I can't install it on my host. Go figure. Yeah, so that's an interesting moment. The UEFI, we're going full UEFI with no BIOS legacy mode more and more. That may vary from vendor to vendor. Some vendors will support Linux, we'll see. Then we have these neural processing units, or NPUs. That is what was it? Intel's like Mirror Lake is one of those. We're seeing a lot of the software vendors. Microsoft has not only their replay, which they're getting some flack for, but other AI-based technologies that they're pushing, and they want to be able to give people some kind of AI assistant on their machines, but that AI is memory intensive, computationally intensive. And so we're seeing a need, just like we saw with the emergence of high-end graphics, a need for specialized hardware to handle those graphics. We're seeing the need for specialized hardware to handle the AI assistants. Right now, they're looking like chips that are systems on a chip that are going to be on the motherboards. Will they eventually become like their own standalone cards, not unlike what you get at the server level? Probably, we'll see. For right now, we're just getting these like system on a chip chips soldered to the motherboard. But yeah, they're called neural processing units, and they're specifically for AI. And that's another reason why I kind of hesitate to buy a new motherboard. It's the NPUs are still they're nascent. They're just kind of coming into their own or being developed. So waiting a few years to see where they go before buying a new motherboard seems, at least to me, for me, a good idea if I can avoid it. And then we have this, it's called back attachments to motherboards. So if you ever look at the bottom of a motherboard, there is actually a lot of wiring. I mean, your motherboards are at least 8 layers deep. And there's layering, there's wiring at different layers, each layer of the motherboard. And then again, because of that, someone realized like, hey, why not just, add more devices to the other side of the motherboard? It's wasted space if you don't. The thing is, you have to have cases that can support that. And we are starting to see uh, vendors making cases that can support back attached motherboards. So the motherboards are changing. We're getting this idea of using all sides of the motherboard. We're getting NPUs that add, AI chips to our systems. UEFI is going full TPM mode at the behest of Microsoft, which means that our legacy options are, the first time I ran into that, I've been installing, Windows on computers in the same manner for decades. You just grab an ISO, copy the ISO to a thumb drive that was bootable, uh, dump the contents in there, restart the machine, make sure you got the boot order in the right sequence, and it'll boot to USB and you can install Windows. That is not supported by that works when the UEFI is supporting legacy mode. It does not work with the it does not work with the new security requirements. And the first time I tried it, the install would fail, and it didn't tell me like, hey, you're using an invalid or unsafe USB stick. It just gave me these weird install fails. That took a little bit of digging to figure out what was going on. So yeah, it's an interesting moment in hardware that we're encountering. And PCI 5, PCIe, I'm sorry, is 5 is here. That's pretty cool. We're getting up to like a theoretical 12 gigabits per second on M2 on an M.2 SSD using PCIe. But we're actually the limitation there is now becoming how much power they can the M.2 specification provides. So that's going to be a moment where I'm guessing that the M.2 is going to have to get updated to provide more power. So we'll see. But yeah, we've got better and faster PCIe. We've got NPUs. Kind of some neat stuff coming in the pipe or arriving. We'll have to see how that all plays out. In terms of the next section, we're going to look at hard drives, solid state hard drives, RAM and storage solutions. Any questions from that last section before we move on? All right. Oop. Awesome. I knew what you meant. It's been a long day for everyone. It's easy to make typos. All right. All right, so a hard disk drive is awesome. So our traditional hard disk drives are platters or these aluminum disks that spin, and you've got a read-write head on an arm controlled by a motor, and you write to sectors of the platter. The speed of these is determined largely by how fast those platters spin. You can get anywhere from, on the low end, 5,400 RPM up to 15K plus. Obviously, the faster it spins, the faster you can read and write data to the drive. They come in two sizes, 3.5 inch and 2.5 inch. Now, obviously, SSDs are significantly faster. So, one of the things if someone's got a slow computer, you wouldn't think that this would happen, but I had a client. So I do some among other things. I still support some small office, home office, and just some like ad hoc clients in town. And you know, it's interesting to see what's going on in the world of general computing. But this little old lady, 80 years old, bought a laptop or a desktop. She didn't need a desktop, but she wanted a desktop, so she bought a desktop. And you would think that Dell would not sell such a machine, but they sold her a um, seven, something like 7,200 RPM platter hard drive, eight gigs of RAM. It was just for Windows 11. It Watching that thing try to turn on was beyond painful. So one of the first steps we did was we replaced we updated the RAM and we replaced the hard drive, and the computer got much better. The solid state is much faster than your hard disk drives. But the advantage of the hard disk drives is going to be that they have, generally speaking, larger capacity, especially at the price point. So they're considered more cost efficient. The size of the bang for the buck, so to speak, is going to be higher with a platter drive than it is with a solid state drive. That's one of their advantages. Also, longevity. It turns out that the way solid state drives work when they do so, in order to make to be fast, they have a controller that's basically managing the solid state drive independently of the computer. It's more or less lies to the computer when a read write request comes in. It's like, yeah, I got you. But it's so it'll take, to make everything faster, it maintains the blocks. Like where a platter drive will allow fragmentation, the solid state drives will actually move blocks in order to keep everything together. By doing that, they are doing more frequent erasing, and it turns out that erasing wears down the gates or the circuitry. And so the more read writes you do to a solid state hard drive, the faster you wear it out. So there are some longevity concerns with especially if you're using we're going to talk about here in a minute, if you're using the multi-level cells, which you get like in consumer grade flash drives, where each cell is actually holding 2 bits of data instead of 1. You'll have even more frequent read writes, and they wear out faster. So there's some concerns there. With the platter hard drives, they last longer. They have much larger capacities, especially at the cost point. And from a security standpoint, we can both do secure delete and we can degauss them. So secure delete, when you delete a file from a computer or an operating system, you're not actually deleting it, right? The file system is just a table or a database of entries to where to find files. And all you do when you delete a file, assuming that you've gone through and you've deleted it from the recycling bin too, once it's deleted truly from the operating system's perspective, all that's really happened is you've removed a reference to it in a table, and that space is available, which means that the operating system will at some point go back and write data to that space. But it doesn't do it right away, which means that someone can come by and see what you've done, and it would be pretty easy to, with some forensic software, look at the table and go, where are the blank spaces? Hey, look at those blank spaces. The format of a Word document or an Excel sheet is known. What's there, and you can pull the data out. So secure delete is going through and making many passes. I've heard debates as whether you need to do 9 or whether you need to do like 32. Depending on your environment, your policies and procedures of your organization, you'll have different secure delete procedures, but a minimum of like 9 passes, a maximum of like 32 is generally good. But the point is, you were just writing ones and zeros and ones and zeros, trying to make it so that someone can't come through with forensic software and see the previous state of the gates. Apparently, with the right equipment, you can kind of see past the current setting to previous settings. So you can secure delete a platter hard drive. In theory, makes that difficult, if not impossible, to do. You can't do that with a solid state drive. You don't know exactly what the controller is doing. And degaussing is where you take a degausser, which magnetically fries the disks, so that the data is magnetically erased. It has the disadvantage of making it so that you have magnetically fried the disk. It can't be used again, but the data is unrecoverable. Then some of the degaussers will even punch holes through them, drill holes through them, etc., to add some physical destruction. But that does not work. Neither of those work on solid state hard drives. Solid state hard drives use non-volatile memory. Specifically, they're using something called NAND. It's basically just a form of non-volatile memory. There are two different structures to the NAND they use. There's multi-level cells and single-level cells. Single-level cells, each cell holds 1 bit of data. That makes it's actually very fast to read, fast to write, and it's more persistent. With multi-level cells, you have each cell holding 2 bits of data. That takes longer to write, it takes longer to read, and it wears out faster. So there's a trade-off there, and you'll typically see single level cell NAND in enterprise grade equipment, and you'll see multi-level cell NAND in consumer grade or SOHO equipment. The form factors that we see in solid state drives tend to be 2.5, which is just going to be using SATA, mSATA or M.2. So mSATA is mini SATA. It's used in small form factors. That includes it's using the mini PCIe interface, but with it's using the mini PCIe slot, but the actual protocol being used is SATA still. This is older at this point. You're not typically going to see it in modern equipment unless you came across some like old laptops by chance or something like that. But it is in theory something that's still there, and it's still in the CompTIA objectives, which is why we bring it up. And then we have the M.2. That's the next generation form factor replacing mSATA. It gets complex because they have different quote keys, which basically change the shape of the interface connector. So you'll get different M.2 configurations that look slightly different, whereas mSATA and the PCIe's are going to look the same pretty much in every device. Concerns with SSD. Those blocks of data being kept together are used to increase speed, which is great. The problem is that it's a lot of reading and writing, which means you're wearing out your solid state drive faster. They're also prone to memory leaks when left unpowered for extended periods of time. Now, most of these solid state hard drives actually come with a battery in them to try to mitigate that or reduce the likelihood of that being a problem. But you can't take a solid state drive, it turns out, and just throw it into a drawer and leave it there for 5 years like you would a platter hard drive and expect it to have you're more likely to run into memory problems than if you did that to a platter drive. They are considered cost inefficient, especially at larger volumes. And there are some because of that multi-level cell. Now they've gone beyond multi-level. You can see cells holding 4 bits of data in some configurations. The problem there is because of how they're packing everything together and having a single cell holding multiple bits, they're reaching the limits of what they can do. And as you start filling up a solid state drive, its performance tanks in a way that doesn't happen with platter drives. And due to like the trickery that they're doing behind the scenes to try to get the most capacity and the most throughput. And then there's some concerns about corruption of data with that as well. So it turns out that those numbers that they advertise, especially over 2 terabytes, as you go over 2 terabytes with consumer grade SSDs, there's some trickery going on there that can lead to problems. It may not. Buyer beware is really the message that you should have in your head, that you may not be getting the most reliable. You may not be getting what you pay for, what's being advertised. Another thing is, again, secure delete degassing do not work on solid state drives, so something to keep in mind. Moving on, that was storage. Moving on to memory. A DDR is SD RAM. It's the standard RAM in the industry. It's faster than the Rambus DRAM, often rated in mega transfers per second, or MTs per second. We see basically with the original DDR, they found a way to double dip on the clock. Instead of just sending once per system clock, they were able to send twice on the clock, once at the peak, once at the bottom. Then with DDR3, they managed to, or DDR2, they managed to double dip on that. So they're quadruple dipping, and then they keep double dipping again and again. And every time they do that, they get faster throughput, which is pretty cool. We're also saying it's a slight change in the shape of the memory, how many pins it has. So none of this is backwards compatible. You can't take DDR3 and put it into a DDR2 slot. You can't take DDR4 and put it into a DDR3 slot. Even if it could fit somehow, it won't. But even if you were able to somehow get it to fit, it wouldn't be compatible, so that wouldn't work. But yeah, so when you're purchasing a motherboard or you're looking at building a system, you do have to look at the processor that you want, the motherboard that you're going to use, and then the RAM requirements of that system. In terms of DDR3, something that CompTIA has traditionally in the past liked to ask about is the pin count on these sticks. So I mentioned earlier that we're not going to do like a lot of like everything you need to memorize for A+, but they have in the past asked a lot of questions about it. So thought it would bear mentioning that with DDR3, you get 254 pin, 204 if you're so that basically the 4 and the O flip if you're going from DIMM to SODIMM. SODIMM again being that small outline form factor. It's for laptops, mobile devices, with a max throughput of 17.06 gigabits per second. DDR4 again gets a bigger throughput, taking advantage of the system clock. We're up to 288 pins, 260 SODIMM with a max throughput of 40.8 gigabits per second. Then they have that really with memory. What they have is they have the the PC speed that helps try to make sense of all of this, because what you end up getting with these are like max throughput numbers. What you end up getting with RAM is that there's different RAMs for different speeds. And so even this is a simplification of what would actually happen if you went to buy RAM, right? You would have to look at make sure that the RAM you were looking at was the specific correct type, DDR4 versus DDR5 or DDR3. Make sure you're getting the right RAM for the system. Then you got to look at the speed of the RAM on top of that. And what you'll find is that like DDR3 RAM at the lowest range, like 100 megahertz, is going to be or sorry, DDR4 RAM at the lowest speed, like 100 megahertz, is going to be slower than DDR3 RAM at its top speed. And that all comes down to the system that you're using, the clock speed on the motherboard. But you can't just look at these blindly and go, oh, like DDR4 is always going to be faster than DDR3. There are some edge cases where that is not the case, and that will depend on the equipment that you have. But so when we're looking at these speeds, this is like the highest PC speed available for the specific RAM. So a maximum theoretical throughput of 17.06 gigabits. And then you go to DDR4 and you get a maximum theoretical throughput of 40.8 gigabits per second. DDR5, 288 pin or 262 SODIMM and 67.2 gigabits per second. So DDR RAM is the standard. It is dual inline memory, not single inline memory. And we keep seeing they find ways to eke out a performance gain by taking advantage of getting more data through on each clock cycle. Other types of memory include error correcting code memory, ECC. It has a parity chip on the stick specifically designed to detect and correct errors. It's kind of there are a lot of people in the industry who blame Intel for the fact that ECC is not widely available for consumer grade electronics. Apparently, one of the rumors is that, and I don't know how true it is, but at least it makes sense, that Intel wanted to convince companies not to buy desktops, that they should be buying workstations. And one of the reasons is that workstations typically support ECC. And so CompTIA put the kibosh on ECC memory for decades in consumer grade electronics. However, it seems as we get to like DDR5, for example, the memory's moving so fast, and there are some technical challenges that are going to require us to move to ECC anyway. So despite the decades of and apparently the performance hit isn't all that extreme. So people have run some tests and they're saying that uh, even in gaming applications, you're not going to see a huge performance hit in modern ECC memory. So we'll see. There's obviously still a little bit of a hit, but how much is, in terms of the speed of the read-write operations from the memory, since you have to compute parity. But the idea is that the advantage is that you can detect and correct errors should a bit go bad. And it turns out the universe is not kind to computers. Like a stray proton going through, a memory chip can flip a gate. Now you have corrupted memory. And if you don't have ECC, you don't know that your data is bad. And maybe that puts the system, if you're lucky, that simply puts the system into an unstable state and it crashes. If you're not lucky, you operate now on bad data without realizing that something went wrong. We also have SRAM, or static random access memory. It's faster and more expensive than DRAM, but it doesn't need that. It still needs power. It is volatile, but it's not. It doesn't need the constant refreshing the way that the DRAM does, the DDR RAM. And because of that, you'll see it used. You get basically better power management, less power requirements. So you're going to get it's faster. Because of that, it's a bit more expensive, but it's typically used in things like the cache for a CPU. You'll see it in routers and buffers, etc. So static random access memory, it is dynamic, but it does not need to be refreshed the way that DRAM does. Virtual RAM. So computers, programs are big, operating systems are big. And mentioned before, Windows 10, 11 technically state, even with the 64-bit architecture, their minimum memory requirements are 8 gigabytes. And you will find vendors like Dell selling folks, like little old ladies, 8 gigabit system, 8 gigabytes of RAM on a Windows system. It's a miserable experience, but it can be done. So what happens though if you've got a system that is running out of RAM? Windows will let you install with 8 gigs and run. You're gonna run out of RAM pretty quickly. Even if you're using 16 gigs, it'll depend on what you're trying to do. But when systems run out of memory, things go badly. Applications crash. Systems become unstable. Systems crash. Users get a little upset when they see that blue screen of death. And so someone came up with a brilliant idea of like, hey, well, it wouldn't be ideal because it's not. We have other memory on the system. What if we use it as virtual RAM? And so with virtual RAM, you are using part of your hard drive as if it were RAM. The IOPS are incredibly slow, comparatively speaking, even if you're using solid state hard drives. Actually, one thing about that, it doesn't come up on the test, but the last I have checked, and I'll admit it's been a while, but it makes sense. The recommendation is to not use, if you can, you have a system with solid state hard drive and a platter hard drive. You want to use the platter for the virtual RAM instead of the solid state. Yes, the solid state is even slower. Or sorry, the platter's slower than the solid state, but because of the way the solid states again do that block writing, you'll wear the solid state hard drives out significantly faster by using them for virtual RAM than you would a platter hard drive. So there's something to think about if you've got a system that only has a solid state hard drive. If you're using virtual memory, and it's especially if you have a large amount of virtual memory, you are reducing the lifespan of your hard drive, in some cases by years. So something to keep in mind. In Windows, the virtual memory is saved as the page file system file. It's just at the root of the hard drive as C:\page file.sys. It is a hidden file, so you have to enable, seeing hidden files to see it, but it's there. Now, Windows automatically manages the size of the page file, and it's generally recommended, unless you really know what you're doing, that you just leave it be. And then with a Linux, typically you'll see Windows doing um, approximately like 1/6 to 1/8. So whatever how much RAM you have, it'll typically take like an extra like 115% ish, 100 and not quite 110%, 120%. It doesn't quite go that high, but I think 15% ish extra memory. Linux has what's traditionally been the swap partition, where they actually take the that section of the hard drive and put it into its own separate partition. You typically find it at dev SD. That X means, so with the Linux disks, it's like dev SDA, SDB, etc. So you would have like your letter, then a number there denoting where it is, which hard drive it's on, and which partition it is. You can also do just a swap file instead of a swap partition. So that would also just kind of like, just like with Windows, the page file is at the root of the C drive. Here, it would just be a file in the root directory. There are certain applications where that actually is somewhat advantageous, but as a general rule, um, Linux is assuming that the page is a block device, and so you'll actually get a performance hit generally. I've heard some people say that like with Logic Volume Manager, using a swap file might make sense, but um, it's one of those things where it's expecting a block device, so doing this that way has caused some problems in the past. I know Linus Torvald was a big opponent of using a swap file. That has been, again, some years since I looked up his advice on that. I don't know if modifications to those rules have changed, but do know that in Linux you can do a swap partition or you can do a swap file. If you're doing a swap partition, you expect to find it with your hard drives in the dev folder. And if you're doing a swap file, you'll find it at the root of your file system. In terms of installing RAM, things that you have to consider include knowing how, trying to figure out how much you're going to need. Windows officially says it only needs 8 gigs for a 64-bit system. That's textbook. It's not reality. And then determine, how much RAM is, what are you doing with the system? Are you gaming? Are you just web browsing? Determine how much RAM is supported by your motherboard, including the speeds that it supports. So you're going to have to, RTFM and actually read the manual here a little bit. When you're making these decisions, you don't want to just wing it. It'll end badly. General recommendation is to not mix speeds. It might be possible. So if you are mixing RAM speeds, there is at least a chance that the system will pass post and you'll actually get up and running. There's also a chance that it'll just freeze and or crash every couple minutes. So it's one of those, you in theory might be able to get away with it. It's not a good idea. In terms of on laptops, it's always fun to install RAM on a laptop. The location varies. Again, you're going to have to probably read the manual and see where that is on that specific model. There's some laptops have a panel on the bottom specifically for RAM, access to the RAM. For some of them, I've seen it behind the batteries. I've seen it, just seen it behind the batteries. I've seen it on a panel. I've seen it behind some other components where you have to take off the whole bottom. I've also seen it behind the keyboard, where you have to, pop the keyboard off. Make sure you don't tear that little ribbon that connects the keyboard to the motherboard. They are, even knowing they're short, they are surprisingly short and easy to damage, as it turns out. Ask me how I know. Oops. Yeah, but you'll find it in a couple different places. The easiest thing to do is to read the manual and see where the RAM slots are. In terms of troubleshooting memory, bad RAM causes your system to crash at unpredictable times. But you'll notice that it tends to be when something memory intensive is occurring. Either you're loading like a large application, or an application is doing a lot of number crunching, or you're copying large files and your system blue screens. um, you know, Windows claims, and they do offer this memory diagnostic tool. The good news is, so you all, if you're doing your continuing at your credit, I know Jovina is doing continuing credits, already has A+. I assume that is the case for you as well, Porny. But so if you taken the test, you know that CompTIA has like their own set of rules or logic, and in CompTIA land, as I like to call it, um, it the memory test, the memory diagnostic tool tends to work. So if you get a question about troubleshooting memory, they're very rarely going to do what happens in the real world, which is the replace and pray method. You're like, okay, I think I have a bad stick of RAM. I'm just gonna pull one out and try it and see if it crashes. Pull another one out. Okay, it didn't crash. That's the right stick. Or oh, it's still crashing. Put that one back. Pull out the next one, and just kind of process of elimination until you do that task where the system doesn't crash. It's always fun. I'm from the GRC. It's insights. Oh, okay. Well, I'm not sure what GRC. I'm not familiar with that, but on a positive note, we've been talking about hard drives, so I hope that has been education.
Yeah, it's governance, risk, and compliance role.
Pardon me?
So governance, risk, and compliance.
Okay.
Yeah, so it's good to know about these things with regard to the risk.
Yeah, and
So that's the reason I register for this. It's
oh,
interesting.
well, welcome. Um,
Thank you.
So then one thing that you missed that I said earlier is that we are I'm good news, bad news. If you took like a whole class on like for this exam, there'd be a lot more detail. We'd be going through just minutia of things to memorize. Here, because it's a webinar and it's only 2 hours, we're kind of keeping it at a slightly higher level, which is good. Hopefully what we're talking about with the hard drives will be sufficient for you.
Yeah.
So yeah, like on the test itself specifically, they tend to focus on this idea that these diagnostic tools work. Um, in the real world, we tend to do more of the replace and pray, where you just have to kind of keep going through and pulling out a memory stick and doing that thing, that running that application, copying that file, and you'll eventually pull a stick where the system doesn't crash, and that is the stick. But you can run the Windows memory diagnostic tool. It tends not to find the mistakes or the errors in the memory unless they're like really severe, but it's there. In terms of external storage, we have a couple different options. So what we've been talking about are so far have been like hard drives, and the assumption has been that you are using internal storage. But we have other options. So one of them is direct attached storage. This is where you would take a hard drive, typically in some kind of enclosure, and you would plug that into your system, probably via USB port at this point, but through any kind of external bus that it might support. If it's a Mac system, maybe that's Thunderbolt or FireWire or whatever. But you connect it via an external bus to the system, and treat it as if it was just another hard drive. Network attached storage, or a NAS, those are ideal for kind of what's called a SOHO environment, small office, home office. A NAS will run you somewhere from a couple $100 to a couple $1,000. It just depends on how many bays you want and how fancy you want the controller to be. Some of the NASs will work as a web server, and they'll do other kind of monitoring and statistics and have other applications on them. But at a minimum, it'll control the memory, and it will provide you with typically a RAID controller. So RAID, we're about to see here in a second, is a way to get redundancy at the level of a hard drive, that should a hard drive fail, you don't lose your data. To external users, the RAID drive looks like a single entity. They don't get to see all the individual drives in it. They just see the volume that they then write to. So a NAS will run you a couple $100 to a couple $1,000. That's just for the enclosure and the controller. That doesn't include the disks themselves. You'll have to provide your own. And then SANs, or storage area networks. Those are, if you can get a SAN, go for it. Problem with a SAN is that a good one, a cheap one's going to run you a couple $100,000, and a good one will run you in excess of $1 million. You really need to be able to justify a SAN. That's not something you just buy on a whim. But it's a whole network dedicated to storage. Typically, client workstations do not connect to a SAN. That would be server only. But those are our three main types of external storage. I didn't mention before that there's going to be redundancy. When we have data, we don't want the data to go away or to lose the data because a hard drive failed. Hard drives fail. And so RAID, a redundant array of inexpensive or independent disks. I've heard both. The independent doesn't make a lot of sense to me, only because when you put them into a RAID array, they are no longer independent. But RAID 0 requires a minimum of 2 disks, and you stripe across them, meaning that you write half of the file to each disk simultaneously. That means that you have increased your throughput. So RAID 0 actually doesn't give us any redundancy at all. It gives us a performance gain. We're writing half of the file simultaneously. It takes about half the time. I get, faster IOPS on that disk. RAID 1 is mirroring. It's the opposite of that. It's you have 2 disks minimum, and you are doing a mirrored copy of one disk to the other disk, meaning that you are writing each file twice. That gives you fault tolerance at the level of a disk, but you have effectively halved your storage. Now you bought 2 terabyte disks, so you bought 4 terabytes of hard disk capacity, but your volume will only be 2 terabytes since one disk will be a copy of the other. There's actually RAID 10 or 1+0. That's where you combine RAID 1 and RAID 0. So you would need 4 disks at a minimum. You would write, half of a file to each disk, like the first 2 disks, like you would in RAID 0. And then like RAID 1, you would copy that across the bottom 2 disks. And so you were getting 4 disks, you were combining striping and mirroring into a single volume. RAID 5 requires 3 disks. You write a third of the file to each disk, and then each disk also has a layer of parity. Parity is metadata. It is parity uses logical trickery to reconstruct the data, but it doesn't take up as much memory as the data itself. So you can save the data, but get a performance gain compared to just mirroring. Now it takes a while to calculate the parity, so your writing is slower, but there's a trade-off there. RAID 6 is similar to RAID 5, only instead of 3 disks, you need 4 disks. And you're going to do, each disk will have 2 layers of parity. So with RAID 5, if a single disk fails, the volume stays online, and people can still read and write to it. It's in a degraded state. The performance is going to suck. You're going to have to, you can have like a 4th disk in there as a hot standby, or you'll have to yank a drive out, put a new drive in, and it'll start rebuilding the RAID array. It's not a quick process, 12 hours, 18 hours. It depends, but you should expect it to take at least a business day. And in that time, you will be in this degraded state, but you can still access the data. RAID 6 is 4 disks with striping again across all 4 disks. And now each disk has 2 layers of parity, meaning that if 2 disks in the array fail, you can still recover your data because each disk has the backups for 2 different disks. So those are our RAID levels. When you're using something like a NAS, for example, you would certainly expect to have RAID in the background, and then storage area arrays will also back up their files or do backups of the drives as well. All right, moving on to peripheral devices, including keyboards, mice, monitors, and printers. So the ports that we see on modern computers include It could be a serial port. You could still run into one of those, I suppose. Every time I teach an A+ class and I joke that you'll never see some old antiquated piece of technology, someone in the class has a story of where they are using some old equipment somewhere in their environment. And we do have, legacy systems with legacy applications. One of my buddies works with the Air Force, and they are finally trying to get rid of some of these COBOL systems because the number of people that can, everyone who knows how to maintain them or fix them is dying at this point, is what it really boils down to. They realize, like, this isn't, can't keep doing this for very long. We need to move off of this. But you do have legacy systems, old hardware to run these legacy applications. So you may still run into the serial port. I mean, they stopped making modern equipment with it 15 plus years ago, but so that's that old classic serial port with a little D bracket on it that you would use to plug in like a printer or VGA monitor, for example, or if you were doing enterprise networking to connect, a plug into a router or switches console port. So those are kind of iconic, but going away. The USB, the Universal Serial Bus. It's amazing how much that has revolutionized computers. We've taken for granted just how much we can do with those things. You can get 127 devices per interface technically, and then you have the following power requirements. So USB 1 or USB 2 can provide a maximum. Each one of those USB ports can provide a maximum of 2.45 watts. USB 3, 3.1, 3.2 can all provide 4.5 watts. And then there's this new standard of a USB power distribution. I'm not sure where you would see that. I guess it's technically used with USB-C, but it can provide up to 100 watts. You'd have to have a power supply unit that could actually, produce 100 watts. But in theory, perhaps if you'd see that when you're plugging in from the wall outlet to, like, for your cell phone charger. But on an actual computer system, you'd have to have the power supply that can provide the PSU that can provide that kind of power to the bus, and a motherboard to support it. So that's it's in the documentation. One thing with USB that gets kind of weird, these power requirements, these are only true if you want to be a USB certified. If a manufacturer wants their device to be USB certified. What you see in the real world is that most devices are not USB certified. And in fact, they ignore these rules. And they provide more power, for example, than the standard allows. And the reason for that is they don't want, pissed off customers. People don't like it. If I plug a device into a USB port, and I know the USB port has power, and the system doesn't provide power for the device, I get annoyed. And people tend to get grumpy, and they try to blame the vendor, and vendors want to be able to sell devices that people want. And so a lot of vendors have decided just to ignore these strict requirements in order to make their customers happy. So yeah, when you're looking at these requirements, again, this becomes kind of an academic thing, or if you were in an environment where you had to use USB certified equipment, then it would matter. And like for most of us in our day to day, these numbers are not actually going to be what we encounter. We'll find more power available to us. In terms of keyboards, we have the layouts, and there's more than just the QWERTY and the Dvorak, but those are kind of like the standard. The QWERTY is the standard, Q up by your left pinky, P over by your right pinky. You've got your home row with the little knobs at J and F. It's in your standard keyboard. Unfortunately, that apparently isn't very efficient. And the story goes that it was designed to deliberately slow typing down back with typewriters, so that way people couldn't jam the typewriters. I don't know if that's true or not, but that's the story that's been passed around for a while. Point is that it is deliberately slow. The Dvorak was designed to speed up typing. And one of the things it did was it looked at the keys that are typed the most, pressed the most, the letters most common in words, and it put them on the home row, so you don't have to move your fingers for them. I at one point tried to learn Dvorak. I'm too used to QWERTY. I can't. I'm sure with enough commitment I can make the jump, but then every time I went to someone else's keyboard, I wouldn't know how to type again. So yeah, you gotta sometimes cut your losses. You can have connectivity in terms of both wired and wireless keyboards. Wired keyboards have the advantage of being less prone to disruption, either due to environmental factors, or just having like the battery on them die. Uh, Wireless is obviously more convenient in a lot of environments. There's also a security risk with wireless. You can buy like a little device that looks like a cell phone charger that will in fact charge a cell phone, but it'll also steal keystrokes from wired keyboards in the environment. And as it turns out, now they have AI that it's a proof of concept. We'll see what comes of it, but someone on a proof of concept trained an AI on a specific mechanical keyboard. And I guess the keystrokes were different enough that the AI was able to read their keystrokes by listening to the sound that the keys made. Something to look forward to as AI becomes more and more prevalent in our lives. Speaking of keyboard mechanisms, mechanical is, they're heavier. They have a more tactile feel. They're sturdy. They're durable. They take a little bit more effort, and you tend to type slower on them. You have the membrane based. It's just a little membrane that is used to record the keystrokes. It doesn't really provide that tactile feel, and some people really hate them. And as a comp, but they're slow. They're small form factor. The keys are very tiny, and they don't really move as you press them. In between is the scissor switch, which is technically actually a form of a membrane, but it has that little like plastic scissor structure, and you press down, and the key gets a little bit of bounce, so you get a little bit of tactile feel. It's still relatively small form factor, especially compared to a mechanical, but people tend to prefer it. The problem is that those little scissor switches can break. In terms of mice, mice tend to be rated by their dots per inch, DPI, or counts per inch. It's basically a measure of sensitivity on the mouse. The higher the DPI, the further the mouse will move on the screen for every inch that you move the physical. For every inch that you move the physical mouse, the pointer on the screen will move further with a higher DPI. The polling rate measured in hertz is how fast the mouse is reporting its location to the computer. So a higher polling rate means you get a smoother scrolling experience or smoother cursor movement. It's obviously ideal for things like video games. And then in terms of the sensors, you can use either optical or laser. Optical is LED, relatively cheap. Reliable, but does run into problems on glossy surfaces and also on transparent surfaces. Laser is more precise, more expensive, but works on a range of surfaces, including glass. In terms of monitors, you got the good old CRT, the cathode ray tube. Those are like the old traditional monitors, the big heavy things. Don't open those, by the way. Those tubes retain quite a charge, and they can kill you if you don't know what you're doing when you touch the insides. Then you got the liquid crystal display, or LCD monitors. You have an LCD panel, so it's got two parts. You have an LCD panel that creates an image, and then you've got a backlight to illuminate that image. If you've ever seen an LCD panel, like the backlight goes out, like if you look at it at the right angle and you squint, and you can kind of see that an image is being drawn, but without the backlight you can't see it. So the backlight in most modern LCDs is going to be LED lights, and that replaces the older CCFL, that is cold cathode fluorescent lamp. It's older technology. The one of the advantages here is that the LEDs use DC electricity, while the CCFL used AC electricity. So laptops, for example, you've got AC from the outlet. It's being converted into DC in the power brick, then converted, so it hits your motherboard, but then you have to have a converter back on right before the bezel to convert some of that DC electricity back into AC to power the backlight on your laptop. By using LEDs, you can get rid of that component, and that just becomes, you're removing a single point of failure, you're becoming more energy efficient, and you're becoming more compact. You need less complex circuitry on the motherboard of the laptop. Then you have OLED, the organic light emitting diode. So you've got like 2 layers of glass, and you've got an organic compound in between them. Compound produces light when exposed to an electric charge. The cool thing there is it's emitting its own color, so you don't need a backlight. Solves this problem even further. Also, each pixel can truly be turned off in a way that LCD still has like a faint glow. So you get a much better, truer black, which gives better contrast. And they're more expensive than LCDs. They're also more flexible. So you'll see these in like cell phones and other, you'll see them in like cell phone screens. You'll see them in the viewer of like some modern cameras and stuff like that, but it is a little bit more expensive than going with an LCD. So you are still seeing LCDs used in laptops still. Printers. So there are a couple of different printers that'll pop up on the A+ exam. You've got thermal, impact, inkjet, and laser, and they'll even make a mention of 3D printer. They're not going to talk about 3D printers on the test, except knowing what they do. I mean, basically they make physical objects, right? We've all seen at this point a 3D printer, but those are varied enough, and there's complexities, what materials you're using. They're not going to cover those on the test itself. One should know there is a difference between a printer and a print device. This is one of those like weird academic things. It's not entirely academic, to be fair. So the thing on a desk that we use, that we put paper into and we put toner into, and we turn it on and we send print jobs to it, and it puts ink on paper. That thing is not a printer. That thing is a print device. We all call it printers, and like the nomenclature, that's just the nomenclature is to call it a print device. In the IT nomenclature, in the vernacular and everyday speech, we just call it a printer. So yeah, it's just the nuance. You can see this though when you go to print. So yeah, the print device is the physical thing. The printer is a software object that then connects to a print device to do the printing. And you can see this when you go into your computer and you go to print. Even if you've never installed a printer on your system, it'll probably give you the option to print to PDF. And there's a PDF printer. There's no physical PDF printer, right? It's just a thing in software. So yeah, or you can have a print server. Now those can actually be hardware, or they can exist in software as well. But you can take a single printer and point it at a single print device. You can have what you would do like in a Soho office, but you can also take multiple printers and point them at the same print device. And the advantage to that would be, I could give, let's say, HR. I give HR the ability to print in black and white, and I give sales the ability to print in color. What I'm doing is I'm pointing, I'm giving HR permissions to one printer, one that is configured to only print in black and white. And I'm giving sales permissions to print to another printer that is set to print color, but I'm pointing both printers at the same print device. So one group will be able to print in color, the other won't. Or I can actually take a single printer and point it at a bank of physical print devices. So that way, if I have an office where I need a bunch of jobs being printed, people don't have to wait for a very specific machine. Order goes to the print server finds the first device that's free and sends it there. So there are some differences between printers and print devices that come up that are relevant. And the terms sometimes CompTIA acts like they're aware of the difference, and sometimes they ignore the difference. I've seen them do both. You never know. How the computer talks to the printer matters. There are different print languages that can be used. The page description language, or PDL, is a very concise way of explaining where, describing the location of where a specific pixel should go on a page. It scales well and allows you to express information about color, shapes, fonts, etc. Adobe PostScript, on the other hand, now that's more of like it's actually programmable. So it's a fairly powerful language, and you'll see this used in professional publishing houses and other kind of marketing environments. Versus HP, so that's more enterprise. And then HP printer control language is specifically designed to emphasize efficiency and the ease of implementation when communicating with a printer. And so it's specifically designed to work with like Soho environments, again, small office, home office. So less enterprise, more small and home office, where Adobe's PostScript is more enterprise level. That print server mentioned before, that can exist as a hardware device that you connect to the network, or it can be a software device. And in both cases, users have to talk to the print server, and the print server facilitates their communications with a print device. Another thing that a print server does that's not on that list is the print server also manages the printer queue. It's not, that's on the, but it also hands out drivers. So if your computer doesn't have a driver for a specific printer, in theory, the print server should be able to hand it out for you, provided the print server is appropriately configured. Printer spools is where the queue is saved into storage while waiting to be processed. The printer queue is the list of documents waiting to be printed. When you print, you have an option for half duplex or full duplex. That can cause some confusion for folks. If you're doing half duplexing, you're using one side of the page. If you do full duplexing, you're using both sides of the page. Printers usually have settings for print quality as well. If you want to do a draft mode, for example. In terms of the printers that come up on the test, you still do see impact printers in use in the world in some locations, in some environments. But when you think of an impact printer, you should be thinking of like a dot matrix printer. You've got a head with pins, and you've got, and you can see here, typical is either 9, 18, or 24. The more pins, the finer the finer the quality will be on the print job. You take an ink ribbon, you put it between the head and the paper, and then you send an electric pulse that causes those pins to jump forward. They hit the ink and then smash it into the paper, printing onto the paper. So that is an impact printer. It's good for receipts. It's good for those carbon copies. It does have its uses, but the print quality is not very high. Inkjets are actually vaporizing. So you've got the ink, and what it does is it actually, again, an electrical impulse comes in, and you've got a heater, and it superheats like a droplet of ink and turns it into vapor. And as it goes through the nozzle, it immediately cools, turns back into liquid, and gets applied to the page. So yeah, the print head is literally vaporizing ink and then spraying it onto the page. As the vapor leaves the ink head, it cools as it hits the air, immediately turns back into liquid. We don't need to worry about the nuances of the carriage system, but understanding how this works, where you've got the paper coming in, you've got a print head with a reservoir, you've got a line here that is sending an electrical impulse. This print head is vaporizing ink, and as it comes out, it gets applied to the paper as liquid. And then we have the rollers to manage the paper and make sure that it is going, through the printer. In terms of maintenance on an inkjet printer, you have a couple options. One would be to replace the inkjet cartridges. That is probably the most common thing that has to be done. When the heads can get out of alignment, when that happens, you can run a realign program that will simply try to get them aligned with the paper. You may have to clean the actual print head itself, and you also have to check your sheets. The rollers. If the rollers aren't working, there's a problem there. The sheets are sticking. That can cause problems with printing as well. Laser printers become a whole process that gets tested on relatively heavily on the A+ exam. It's actually kind of a neat thing. So you have this drum in the center of the kind of at the heart of this. And that drum is photosensitive. When it's exposed to light, its magnetic properties change. And so what you'll do is, you can see down here, you have corona wires charging the drum. So as the drum rotates, you have these wires that give it a negative charge all over. So it's got a uniform charge all over the surface of the drum. Then, when the print order comes in, the laser etches what's to be drawn in light. And as the light hits the drum, it changes its magnetism. It went from negative to less negative, so relatively positive compared to the rest of the drum. You then expose it to toner, and that toner has metals in it that are attracted to the positive areas of the drum, which were those parts of the drum that the laser went over. So now the toner, leaps onto the drum and is in those spots that the light etched. You then actually fuse it or melt it. First you're on the drum, then the drum will come around, it'll get put onto the paper, and then it literally gets melted onto the paper, which is why when it comes out of a laser printer, the paper's hot. So yeah, you're taking the toner and it's getting attracted to the drum where the laser went. It's then being transferred to the paper and then melted onto the paper. You scrape any residue toner off, you recharge the drum, and you just keep going. So that is and obviously if you have color printing, you'll have to have multiple passes for each color. You'll have different drums, one per color. So it's a little bit more complex with color printing, but the idea is still the same. In terms of some of the components that we have back here, yeah, so the processing, the bitmap file is dot by dot etched onto the drum. First, you got to charge it, then you expose it, then you develop it, then you transfer it, then you fuse it, then you clean up, and you do it again. In terms of laser printer maintenance, one of the first things, so they'll give you kits to help you manage laser printers. It's always a fun job to do. No one likes working on printers in IT. That's like a universal. But you have rollers at different phases of the printing process. And each one of those rollers can become damaged. They can wear out. If they wear out, they're no longer able to pull the paper. They could get condensation on them, in which case that paper starts sticking to them. They can get dirty. If they're dirty, they might not grip the paper correctly. You can just straight up replace the toner cartridge, which is lovely, but you'll typically need like a little vacuum to help get leaked cartridge toner out. And stuff's pretty toxic, so you'll want to use a proper vacuum or like a damp cloth and try to avoid letting it touch your skin. Thermal printers, on the other hand, are another type of printer. They're kind of neat in that there's no toner, there's no ink, there's no ribbon. you've got paper and you've got a printer head, and the printer head has small little heating elements in it. And all you're doing, you need a special kind of paper, but you heat up the paper, and um, it as the paper gets exposed to the heated elements, that basically those areas turn black, and so you're painting the image to be, or the text to be written with heat, and it turns the paper black in those spots. Uh, so it's kind of neat in that sense. It has the disadvantage that the paper is sensitive to both heat and light, which means that it doesn't last very long. You ever get a receipt, put it in your pocket, and it's like a warm, hot day. You're warm and hot. You get home, you look at your receipt, and it's just no good. You can't read it. That's because the paper is heat sensitive. If you leave it out on a desk for too long, and especially if direct sunlight hits it, it fades out. So basically, what they're going to say is that this thermal paper is not suitable for any kind of application or environment where you need long-term archiving of printed data. It won't last. Motherboards and CPUs. So, sorry. We'll skip over this relatively quickly since this isn't the A+ exam per se. But the ATX, Advanced Technology Extended, was a standard for motherboards. It's been around forever. It has the advantage of it was developed to increase airflow over components. So heat is the enemy of computers. It's always been the case. And someone realized, like, hey, if we structure a motherboard, and we put the RAM and the processors in a certain orientation to each other, we can get maximum airflow through the case. And so that's what ATX does. And so yeah, now you'll hear about an ATX case. It's a case specifically designed to hold an ATX motherboard. You hear about ATX power supply units that are specific. So the ATX standard actually specifies not just the motherboard, but the power supply units for that motherboard. The standard one's actually pretty big, 12 by 9.5 inches, more or less. But they can hold up to 7 PCIe slots, typically 4 slots for memory. It's a fairly large desktop slash workstation motherboard. Micro ATX or MATX, 9.6 inches by 9.6 inches with 4 PCIe slots and 4 DIMM slots for memory. So this is still a decent computer. 4 slots for memory, 4 PCIe slots, but it won't take up as much. The difference between ATX and micro ATX or even ATX extended is going to be, you're going to have like a full tower, or you're going to have just a big computer, or you're going to have a relatively small computer. The extended ATX is designed for like a full tower enclosure. You have the ITX, Information Technology Extended. These were specifically meant for small form factor. So that you can see here 6 by 7 by 6 by 7 with a single PCIe slot and 2 DIMM slots. This is meant for that's like a home theater size computer. So like a computer where you were, this was something that was common on the test for a while, where this notion of home theater computers. Relatively small enclosure, not a lot of airflow, but therefore home theater systems. Nano, you're looking at 4.7 by 4.7, and then Pico, you're getting even smaller. If you were taking the test, you might have to memorize these. What you're going to see is that each one of these, like smaller form factors, they have niches. Are you using it for a Raspberry Pi type environment? Are you using it for some kind of embedded system? Each one of these will have its uses, and again, you'll make sure that the enclosure that you're using matches the motherboard that you're using, and that you have the appropriate processors as well. In terms of choosing a motherboard, you need to make sure that you are using. How do you do this? I typically find the motherboard I want, or the processor I want. I usually find the motherboard I want with a consideration of the processors, and then find a case to hold it. You'll need to consider how much expanding you plan on doing. Are you going to be adding multiple graphics cards? For example, do you need peripherals that still need card space? You have to consider processor support, memory as well. So the processors have to match the motherboards. If they don't work. You'll turn the system on and it won't pass the post. You're sitting there with a dead system. You need to make sure that the motherboard is compatible with the memory that you want to use, in terms not only of DDR3 versus DDR4, but also the speeds that you want. And then you have to consider the power as well. How many peripherals are you planning on supplying? How much power do you need? New motherboards will actually just kind of, so servers, right? In a server environment, the servers have multiple power supplies. Some of the newer, more advanced, high-end like towers for users will have support for multiple motherboards, multiple power supplies. They're going to say that's for like video editing, gamers streaming, stuff like that. But the idea is that all these become factors in deciding what motherboard you want, what case you want, how many motherboards do you want, all that good stuff. In terms of the CPUs, they are the brains of the process. Brains of the processor. They're the brains of the computer, I should say. They do require cache. Cache sits, the lowest level caches sit actually in the die. In terms of the test, it's not getting into the latest and the greatest, but you can see here even there's consideration for, hey, what application are we working with? Yeah, and there's nothing you don't have to worry about on the test, like any of like CompTIA. CompTIA doesn't make you worry about like Intel's codes for the letters and numbers that appear after these models. But apparently AMD just recently upended their, one of the reasons to avoid that is AMD, it was just in the news this past week, 2 weeks ago. AMD has apparently decided to upend their naming conventions. So this stuff changes often enough that it makes sense for CompTIA to like wisely just not torture people with memorizing something that may have changed since they wrote the test. But you'll see as like a typical thing that for an enthusiast, like a high-end user, an i7 or an i9 processor would be adequate on the Intel end versus like a Ryzen 9 on AMD. Mainstream, you can get away with an i7, i5, or even an i3. You'll have to make your own decisions about what you need. For most people, an i5 is fine. Budget desktops, you can actually still use Pentiums and Celerons or a Ryzen 5. For mobile, so you'll still see like i7, i5, i3 listed for the mobile, but those are a mobile variant. Depending on the processor, there is a significant difference between its mobile and desktop counterparts. So some of the mobile versions will actually have Wi-Fi wireless NICs built into them. So you don't need like a separate device or chip. You'll see the same thing on AMD. The Ryzens have both mobile and desktop variants. Servers, Xeon for Intel or EPYC for AMD, and then Xeon or Ryzen Pro for the workstations. In terms of installing a CPU, one of the biggest things is making sure that it fits the motherboard. You've got the right processor, type of processor. You have to put it into, you want to use what's called zero insertion force. Like almost every modern motherboard will have this. It's a lever. So you put the chip down, you'll make sure it's positioned correctly. There's usually like an arrow on the chip that lines up with the, you'll see like the indicator on the motherboard, and you get it in right, and then you take the handle and you can push down. And the nice thing with using the zero insertion force is that's there to prevent user error. What you don't want to do is bend pins. If you bend pins, the worst thing you can do is bend a pin on the motherboard. That would be really bad. If you still don't want to bend a pin on a chip, but probably better to replace the chip than the motherboard, depending. You can obviously try to straighten them out, but you don't want to bend pins if you can avoid it. So a zero insertion force handle makes that harder to inadvertently bend pins. You'll apply thermal paste. A little bit of thermal paste goes a long way. If you use too much, you can get it to like spill over, then it gets under, and then it fries your system. That's bad. So it's a little bit of thermal paste. The thermal paste provides a conduit that helps connect the top of the processor to the heatsink. You're going to want to heatsink some kind of passive cooling. So you have different kinds of cooling, passive versus active. Passive is using just raw physics. you're touching the processor, and heat through that physical contact is getting drawn up. Then you'll blow air across that. So you'll combine passive and active. You can use liquid cooling. Mainframes and servers use liquid cooling extensively these days, but it can be used um, internally at like desktops and workstations. Be careful if they spring a leak. That's liquid getting all over your electronics. But even there, the liquid is active. You've got a reservoir of liquid cooling with a pump that's being sent through your system. But at the end of the day, you still have to have fans because you're going to try to get that hot liquid to a point where a fan can then blow air across it and try to get a transference out of the system into the air. Versus Intel versus AMD. Intel uses the LAN grid array or LGA chips. These have the pins on the motherboard that allows you to have a higher pin density. AMD, like the AM4, is a pin grid array. There, the pins are on the CPU itself. That provides durability for the motherboard and is also cheaper to produce, but the trade-off is you don't quite get the pin density that you would have with Intel. Power supply units. One thing here you should know about them is they have efficiency ratings. Basically, that tells you how efficient they are. What does that mean? Well, they're pulling 120 volts, out of the wall. The wattage is a product of the voltage and the current. You have a set amount of voltage, in a standard room, for example. Obviously, in high-end environments, you'll need a unique situation with your utilities company, but question becomes how much, you have a certain amount of wattage available to you based on the current and the voltage. How much of that are you able to turn into DC power? Because you're going from AC to DC, there's going to be a loss there. When it's lost, that's just energy, that's electricity you're paying for that you're not getting. And it also puts a limit on the power supply units that you have available to you. So a platinum rating is 90% efficient, gold is 87, silver is 85, and bronze is 82. In terms of the rails that are available, you got 3.3 volts, 5 volts, and 12 volts. That 5 volt tends to get used with, or 3.3 volts tends to get used with some of the smaller chipsets that can help power the BIOS or the UEFI chip, maybe the RAM, and maybe an SSD. And the 5 volt is going to be for your USB ports, any kind of card reader, optical drives, cooling, LED lighting, and your 12 volt rail is going to be for the motherboard, the GPU, and liquid cooling. Nope. It is now 7:30. So we have reached our quitting time. Thank you all so much for attending. What you need to do, Courtney, is to email, I think it's helpdesk@trainingcamp.com and get a certificate of completion for your time here today. No problem. Thank
Sure.
you,
Thank you
Jovina.
so much, sir.
I'm glad you made it. Sorry, it was a small group, everyone, but hopefully you learned something.
Yeah,
And
I
you
did
got
pick
some.
up some points. Thank you very much, sir.
You're welcome. Have a good night.
You too. Bye.
All right, everyone. Take care. Good. I'm glad. And you got yourself some CEUs to boot. So have a good night, and good luck getting the rest of those credits. Take it easy.